Sedaj pa sledi presenečenje večera, kaj ne, Eva?
Res je, Miha, kdo je to?
Kolikor vem, ne prihaja iz Evrope.
Ja, res, to je konstruktor trenutno verjetno najboljšega letala v 18-metrskem in 21-metrskem razredu. Na oder vabim Uysa Jonkerja.
Hello, Mr. Uys Jonker. We are pleased to host you here. We are really excited to hear how you did such a nice plane. The stage is yours.
Thank you very much. Good evening, everybody. It's a pleasure to be here, and thanks Uys and Jadralnega who invited me. It's always nice to visit Slovenia. English is not my first language, and I think it's also not yours. So if we don't understand one another, just tell me to slow down or to say it in Slovenian language, if you will help me. Okay. Now after Peter's presentation, I am in a little bit of trouble. Nobody can have that visuals and that excitement that he's got, but let's see what we have here. So hang on, maybe it's fun. Could I get the sound? Ladies and gentlemen, different to Peter's presentation, I'll explain a little bit where this technology came from and how we developed it. So hopefully we give you some information of how things can be done. It started actually a long time ago, almost in the 1970s, when two young boys, our chief design engineer, Uyys Jonker, started with his own product. You can see there on the left-hand side was his first aviation project that did not fly at all, and we still don't know why. And the second one that you see below here was the first kit that we purchased, and when we built that, it actually flew. But this was all inspired by the construction of a wooden glider somewhere in a shack in Africa. My chief inspirer and dad, my Uyys Jonker. And you can see how he's busy cutting the ribs out there out of plywood. And his workshop wasn't that fancy. If you look at the roof, it was actually not well designed for all weather conditions. In this specific picture, he's busy to ream the main pins of putting this Turner American design glider together. And while at the same time our boys paid all our attention on polishing our finishing skills. As you can see there, that was our first joint venture, a project of two little wooden aircraft which we could only paint, they could also not fly. We still work on trying to work out why that didn't fly. You can see there's Ati and myself on the right hand side, a little slightly more hair and maybe less tooth. And the main idea was this, to develop the most sought after sailplane in the world. And by three crazy, I think not just passionate, but crazy enthusiasts. To do something like this, you have to be somewhat crazy. And now 30 years later, what I realized of this dream, and I'll explain to you a little what that was. We've sold so far just over 100 aircraft worldwide. You can see Europe is our main market there, also Australia and America. And the aircraft has done actually fairly well. It's won every single national competition that it competed in. Like South Africa, I think it's now 9 or 10 times in a row that it won the South African nationals, the US, United Kingdom, all over the world. It was very good. And then also in European and World Championships. On the World Championship level, we haven't had a gold medal, but we had bronze and silver in both classes, 18 and 21 meter. And in the European Championships last year, we were quite good. We had 7 out of the top 10 in the open class, including the first 4 positions. So slowly the aircraft is entering European ground and making quite a good success of it. And we at this moment employ over 100 full-time employees, which includes an engineering team of about 12 engineers. And this is where we are now. And so now, any questions? Rasen, you have more time. Any questions? Okay, I'll explain how this was developed. How did we manage to do this without any skills? Basically, when my dad's glider was finished in the 1970s, we were extremely proud. But there was something wrong with it. We did not like the shape of it. It actually looked really a bit horrible. If you look at the shape there, it's just the time when the cirruses and the lapels came out, and we looked at the composite aircraft, and we were not very happy with my dad's attempt, although we did not say anything, that's all we knew. But my brother, as chief design engineer, he wasted no time. He immediately started to redesign an aerodynamic shell around this fat turn. Now, anybody with common sense will understand that you can design a slick thing about a fat structure. But in any case, that was the attempt. And unfortunately, he realized that he did not have the critical skills, the engineering skills, the aerodynamic skills. And this is exactly the reason why we started to study engineering, to figure out how do you design a proper sailplane. And this is actually how we started. Then 30 years, how long was that later? About 8 years later, as engineering students, we started to learn. And every single thing that especially Ati studied was how to design sailplanes. So when we were sitting in the engineering class, if it was about thermodynamics, we looked other way. But if it was about structures and aerodynamics, that we were interested in. But so, the design of the JS1, we started with a clean sheet of paper. We said, what is the requirement to make the best sailplane? And what we said is, okay, let's write a mathematical formula. And this is basically how we design the whole sailplane. Everything we do, we develop a formula, a mathematical model, and from the model we see what the end result will be. Now the end result of a sailplane is basically, you can use this formula to determine it. You basically have the vertical, the climb speed, and then the cross-country speed, and the combination of this is your total cross-country speed. So if you want to make the best sailplane, you have to optimize a formula looking like that. So that every ground speed can be from that formula derived, and you have to try to optimize that formula. Now that is a little bit above me at this moment. I forgot my algebra by now. But in any case, that's a formula to optimize. And if you look at that formula, you can break it down into cruise ability, so that you have a glide angle at various speeds, and you have a climbing ability so that you can always climb. So basically you have to optimize in these things, but it can determine how much focus on climbing and how much focus you have to put on cruise. If you take, for example, a K8, a Schleicher K8, it will beat any single aircraft in the climbing ability, but it has no cruising ability. And if you use some of sailplanes that has fantastic cruising abilities, but lack a little bit of climbing abilities, like I would think of the ASW28 and the LS7 maybe, those were too much focus on the cruising performance. So it's a very fine balance to find the optimize by achieving those two parameters. So the first thing to get this cruising performance well, we have to design a low-speed laminar airfoil. Now our low-speed laminar airfoil looked like that, and we think that's still the best airfoil in the world. And the name of that profile is, if you see there, the T12. Now I can just quickly explain how we developed the T12. We first developed a basic profile based on skills that we've learned from Delft University of Technology from Luc Boermans, and we refined these design methods. And finally we had one basic profile, and we put that in a wind tunnel, We tested it and we realized that the design parameters or the forecasted parameters from the computer software agreed exactly with these from the wind tunnel. So then we started to refine this profile, and the first name of the first profile was A1, and then we did a bit of work, and once we get an improvement you have A2, and then you have A3 and A4 and A5, and we went until A50. Why? I have no idea, but then we thought, okay, we're running out of A, so let's start with B. We start with B1, B2, B3. And every single time you do a small change to the profile, you run a simulation and you see the end results over the complete scope, the gliding, the complete flight scope. And then you determine what that is. Now finally when we reached T12, we could not find any improvements on the main profile. So the main profile consists of iterations of about 50, and still even at this moment we can find no improvements of our basic profile. So we're doing all other little tricks to improve the aircraft at this moment. Right, from this profile we developed 6 different profiles to suit the Reynolds numbers at each area. So the aircraft, I think this was the first aircraft which had multiple profiles at each section. I think nowadays it's common, if you don't do that you'll not be in the race. So the second thing is, what we try to design is to make an optimum plan form. Now the plan form is very important for the climbing section again. So here we selected a ellipse form. If you look at that ellipse, so our wing is basically an ellipse form. If you look at the Spitfire's wing, it's a very, very good plan form because the lift distribution over this wing is always the same. It means that every part of the profile carries the same load. And that's very important. It's like, I don't know if you guys have the army at one stage, but in South Africa at once we had to do some army training. And sometimes you have to carry these massive rocks, you know, and 6 guys have to run with us everything. Now if one guy is shorter than the others, you know, he don't carry his load, you know, sometimes he's even hanging. And that is very inefficient for the group. So you have to have everybody with the same length to be the optimum speed over a course. And it's exactly the same with the wing. You have to have each guy carrying the same amount, and therefore you have to taper this down to the tip, because the guys at the tip must not carry so much, because then your spill over the tip is too much and a lot of drag is created by that. So this is why elliptical plan form is selected. However, we did not select a full elliptical profile because we have the CNC machines to cut that, and the single reason for that was because you will never be able, when you paint that, to have exact profiles around it. So between straight sections you can finish it exactly straight. So we have a 99.9% assumption of an elliptical profile with 100% ability to finish it exactly to the profile spec. That's why you have to have these segments like Shemp has been doing since the discus days. Very good idea of this. Right, so the second, one of the next parts that we paid a lot of attention was about the optimization between the fuselage and the root. This is extremely important because your wing stops there. But suddenly if the wing stops, the lift tapers down and there's a lot of spillover. It's almost like the wing tip. So the same problem you have at the tips, you also have at the roots, where you have lots of spillover and a draggy fuselage that gives problems here. So you see what we have done here is, instead of using the, I don't know if this thing will show that, yeah. Instead of using the normal T12 profile in the root, like that one, which what they call, it's got a very steep pressure recovery region. That means on the back of the profile, if you look at the air going over this profile, over, and at that point, from the highest point, the pressure is not getting less, it must recover the pressure again, and the pressure must increase again, as you can see there. And unfortunately, pressure cannot do that. The air cannot increase itself, so it breaks away and causes a lot of drag being dragged with this profile. Right. So what we had to do there is we selected the different profile, a turbulent profile, because the fuselage in any case makes it turbulent around that area, and we made a much shallower pressure recovery region so that the air has time to stay attached to the fuselage. And then you see what we have done. We've used nice modern design software tools to optimize the flows. So you can measure what is actually happening here. And you can see fantastic laminar flow over this area here, and the laminar flow there, and here you see all the problems and the nonsense coming. So from a designer point of view, we actually like to reduce this to the minimum distance. Why? Because laminar flow, that means the air is not disturbed by the profile, has 5 times less drag than turbulent flow, 5 times less surface drag. So you want to stretch the laminar flow as far as possible. And if you look at our wing in this, the T12 wing, we get 95% laminar flow on the bottom and about 73% on the top section. So it's fantastic laminar flow to make sure when it glides through the air, most of the profile doesn't, or the air doesn't feel the profile. Only the last section behind it does feel it. Right, the next section, we looked at the winglet design, and therefore we used the third generation CFD models. Initially we used hand models for the JS1A and B. We used hand models, but from the C model onwards, we had the tools that was calibrated CFD methods, and CFD stands for Computer Fluid Dynamics. And that is basically a computer wind tunnel. So exactly like you would make with a normal wind tunnel, you define a box in computer space, you select a certain flow, you put your model in it, and it predicts very accurately what's going to happen. You can only do that if you really have calibrated your tool, because the transition from laminar flow to turbulent flow is extremely difficult to determine by software. In any case, we managed that. We had two of our design engineers working for 2 years on their PhDs to develop and to calibrate these tools so that you can use CFD in glider design to predict laminar crossover to turbulent flow. I don't know if it makes sense what I'm saying, so just stop me if I talk too much technical stuff. In any case, the design tools here can determine the drag or the saving of drag that you have in the winglets. And you can see there's fantastic flows. There's almost full laminar flow over the winglets of a modern aircraft that we achieved there. The next one is a fuselage design, which we also use CFD methods to determine all the wind tunnel sections and the flows. In this specific exercise, if you see that little picture there, it's in a side-slip condition to determine what flows will happen over the fuselage section and what will the effects be, what is the structural effects of it. So that is what we achieved there. Typically we use the CFD methods in all aspects. Alright, the next part we come a bit with manufacturing. I did not spend too much time into the CFD, I think I'll get later in the presentation of that. But how do we make these things? Now the method that we use is CNC machine manufacturing. The main thing is you design a model in computer, then you convert this into a code what a milling machine, a CNC milling machine understands, and you cut a mold out. From the mold you make a part, and from the part, the part is required to fly. So, the manufacturing of the molds is done by this 3D milling machine. You can see there we're busy cutting out the tailplane. You can see first the rough out sections here, and then the fine cut. And that's all done because the machines can do it accurately. By hand, it's an impossible job. And then the machining of the positive plugs is made then. So in this case, we machine positive plugs and we make tools from it, with other words, the negative tools. And then the manufacturing, obviously, you start in the tools and build your part. Now you can see it's quite funny. Composite aircraft are different to the manufacturing of other aircraft. You start with your tool, you see the brown part is your tool, and the white part is the first layer of paint in the mold. So you first paint your product and then you start building it. Right, so there we've painted the first product, that's the picture of the prototype. You can see the chief design engineer is a little older, but he's now much less here already. And you can see there where the inside structure is built. You can see the carbon spars over there. If you look at those black pieces, those are the carbon spars. A foam core to give it the stability. And in the next picture you see the ribs and the control systems being built into it. The front section is the water tanks, and the section in the rear for the control systems. And then this is the actual first mold that you open. You can see how excited we were when we opened the molds and there's a wing popping out there. We were extremely, extremely excited. And then on 6 December 2006 we rolled out the regulation. It was one fantastic day. Now I just played this little video because it gives a bit of background of what we have done. It's quite interesting. So just bear this with me this morning. We as young boys had a dream about having our own high-performance gliders. 6 years ago, we officially started with this project working full-time. Everything was a challenge. It's very hard to develop and to design and develop your first glider and to beat glider manufacturers from overseas who's in the business for 80 years. We started with a blank piece of paper and we made no compromises in the aerodynamics whatsoever. Even though it meant that we had huge difficulties in the structure later on in the project, we just took no prisoners when it came to the design of the aerodynamics.
Die ontwerp van die JS1 se airfoils is redelijk verskillend van ander vliegtuie. In die sin dat ons 6 verskillende airfoils gebruik op die JS1. ons airfoil is een van die dunste airfoils wat gebruik word vandag op hoë werkverrigtingssweeftuie. Hy is net 12.7% dik.
What I saw so far and how they prepare for it in terms of inspecting along the line in manufacturing or inspecting parts, making samples, resin samples and everything. So this standard definitely matched the European requirements.
We didn't want to just throw a plane together, you know. We spent days on end on building molds that fits perfectly, you know, just getting the thing perfect.
Until the last minute we had to face small little problems that suddenly appeared from nowhere. Like final attachments we drove through power cables, and we had to now suddenly do some repairs on the glider just before we expect the test flight.
Now we installed the flaps and we saw that the flaps was twisted somehow. We don't know what happened in the molds, and we had to take the flaps off actually. And luckily we had a spare set that we had to spray in last minute and install them, so that was quite a mission.
Nice take.
Hey man, don't scratch the paint.
It was a very emotional moment for me. I cried a little bit, and I mean it's 10 years of actual working on this project for me that came to realization here, and I was just amazed that it looked so perfectly stable.
All controls were harmonized and it felt very comfortable. I decided to take a high aerotow and I enjoyed every second of it thoroughly.
I was just amazed of the beauty of the aircraft, and it was just really beautiful to see it fly.
It's a very emotional moment when it first flew, and it's just a 5-year dream of mine that's come true. So.
Unreal. The JS1 Revelation is Jonker's first glider, and the Revelation nickname the amount of work that was involved in it was a real revelation to our team, and the performance will be a revelation to the competition. I was very brave when I said that last words. I was not exactly sure that was true. Luckily it turned out to be a good aircraft. So the JS1 is the only type certified aircraft designed in South Africa. And obviously, because we have type certification, this aircraft are allowed to fly worldwide. The problem, however, is that most of our aircraft are exported to Europe, and therefore, as the law is now, that aircraft that want to be registered in Europe must have a European type certification. So at this moment, how we're solving this problem is by having a partnership with M&D Flugzeugbau in northern Germany, and together we have applied for the type certification. It's already certified in South Africa, but just to have it recognized by the European Union, we have to have a partner. Now why that? Why do we have to do a double? Because it's already certified according to the CS22 certification standard, but now we have to also comply with the EASA certification. Firstly, the JS1 has an ICAO, that's an international standard recognized type certificate, and it can fly under the South African registrations all over the world. But the EU, this is the European Union, does not allow EASA to accept foreign type certificates unless a bilateral agreement is in place between the governments, and this must be signed on government level, and between the European Union and the South African government, they don't manage to sign this, because the European Union is a little bit unfair. They would like to have a BASA agreement signed. A BASA stands for Bilateral Air Service Agreement, which requires South Africa to open the airspace for foreign airline carriers to fly there. So we would like to have a type certificate approved. EASA wants to have our airline, our airspace is open to fly there. And our government thinks that's a bit of an unfair unfair agreement, and so they're working on it. So in the meantime, we said, while they're fighting this, we're just going to apply for EASA's type certificate with a partner in Europe. Right, so that is basically the reason why our certificate is not approved, because it's on political level that they actually have this arm race, which we don't want to be involved in. Right, so what is it says 22 certification basis? I'll talk a little bit about the certification part of it. Firstly, it consists of a number of things. One of the tricky things is the material specifications and allowable loads. That means how strong is carbon fiber, and how strong is Kevlar, and how strong is glass. And these things you have to determine. And unfortunately, we, as a first applicant, as a type certificate, must come with this data of all these materials forward. Luckily, when we started with this project 15 years ago, we started every year with the university to make samples of carbons and Kevlars and all things. So we have this database. But when we approach our European partners, which is part of the European manufacturing group, they're supposed to have this data. But nobody has it. All the existing manufacturers refer to older design and older one, but there's no clear data. So we had to develop this. Then it consists of flight testing, structural tests, and then all your documentation, flight manuals and maintenance manuals, and then all the placards. So this is the whole group in one sentence, but it's a book this thick that you have to comply to. Now typically, if you just say some of the material tests that we're doing, one of it is impact testing. If you look at it, what this looks like, I must just now get this thing to play, Erasm. So basically, this is a high-speed form of a carbon tube simulating a part of the aircraft, and you determine what is the loads that carbon can take in a crash. This is what material data properties is about. So to take what is the energy that the fuselage will absorb in a crash. So typically, these are some of the tests that we've been doing. Some of the structural tests we do with FEM analysis, that is with hand calculations and with computer analysis. We do structural load tests, in other words, where we push and we pull these things to the ultimate loads. And we do that in the fuselage, wings, tailplane, and cockpit and landing gear. And typically, if you look at the FEM analysis, if you take a fuselage, FEM analysis stands for finite element method, which you do a mathematical method by having a grid over the aircraft, and at each single intersection of those lines, you calculated the forces. So this is a computer method to determine it. But you have to back this up with hand calculations, because a computer always gives you answers, regardless of it's wrong. So we have the FEM analysis backed up by hand calculations. Typically in the fuselage, you can see the pictures you get from FEM analysis is beautiful. You get some pictures with the forces in each layer. It tells you which layer of carbon works too hard in certain load conditions. So in example, you pull the tail in the maximum load conditions and you see where the problems are. For example, when you look at the cockpit crash, it shows you that this layers may be under stress in a certain crash condition, and you have to improve the strength there. So it's a fantastic tool to optimize the fuselage for correct strength without making it too heavy. And then you obviously have to verify your design. You first have to check this computer answers that you get. How does that compare to the hand calculation? So the first job we did is, we said, let's build the cheapest part, and that's a tailplane. We did a FEM analysis on it, and then we also designed what they call a wiffle tree. So you have the tailplane there, and you pull on a single point. You can see always there, and you simulate the air forces on it, and then you compare the results of what the hand calculation, well, what the FEM analysis says with what you're actually measuring. And in this case, you can see our actual model determined that the bend through this, the tip deflection will be 84 millimeters, and the calculation said 83. So this is as close as you can get it with FEM analysis. So this is the methods that you verify that your computer methods are correct, always by hand calculations and by tests. For example, Lots of measurements is done by measuring it for certification. Here we measure the stick forces on the stick. You can see there you have to pull about 31 kilograms of force against the stops, so that helps. Winglets must be pulled to 22 kilograms. You see what you do with the winglet. Don't do it at home. So if you pull your winglet like that, please don't do it. You only do it for certification. You have cracks and things, but you can lose your winglet. And then obviously the main load is the fuselage static load test. Now the static load test we perform by creating a fixed feature on the ground, and then we also have this wiffle tree. So it's a single attachment point, and then you can see the single attachment point is then spreading the loads to all these sections over there. So we made some rips, and that simulates the forces on the ultimate case in the air. We also, I think we also verified and backed this up with strain gauges and computer predictions of what the loads are and compare the results. For this video, I just shorted it because it's too long to see the whole test, but I'll show you the test, but the volume will be a little high, so if I continue this one. Oh, there it is, okay. Okay, first, the strain gauges are that you put measurement elements all over the fuselage and you measure the deflections, and at that you can determine also the forces in the wing. So this is what the test looked like. If you can imagine, we started there on a high spot and the wing was bending down, and this roof of ours is like 6 meters high. You can see how now we're at 1.5, I'm just going to pause it there, and I hope I can play it again. Now, what you require to demonstrate in certification is you determine the ultimate load, and that is, there's a lot of load cases. The guy can fly VNE and then pull the sticks this amount, or you can add either cast lift, and all these things you determine what is the ultimate load. And then you have to demonstrate that you are 1.5 times above that. And if you can, so the safety factor is 1.5 there, so it's 1.5 times the ultimate load that you can see. If you demonstrate that you can do 1.725, then you also reduce the fatigue test that you have to do, and it assumes that the aircraft has got the infinitive structural life. So we have to go to, I hope I didn't start it up again. Just check it from the beginning. So you see, once we're at 1.8, we were very satisfied with the test. And then we check when the wing will break. So we tried now to break this wing. And now we have our 1.5, so that meets the basic system requirement. Now we have 1.8, now that we also meet the fatigue one, and now we see when the test will be, where the wing will be breaking. You can hear our jig falling apart now. And then our jig back. Now we had this one young engineer who designed the test rig. Now I don't want to tell the full story of this, because on the first test we had the whole CAA there observing this, and we had one of the cables failing, and the whole wing came down and smacked into the ground. It was chaos, and we actually just repaired the wings and just a few holes in. There was no structural repairs required, and we were extremely upset. And then we realized, even for test equipment, you have to buy cables with release certificates and conformance statements, because the cable that he bought was just there from the local shop, imported from China, and it couldn't make the loads. So we were highly upset about that. And then in the second round, when the jig failed, we said, why did the jig fail the 2Gs? We wanted to break the wing. He said, no, I designed it for maximum of safety factor of 2, because we never expect the wing to be that strong. But we still don't believe him. We think he just made a calculation error. At least, because we had the safety factor of 2 that we achieved, that allowed the structure for us to develop into the 21 meter in a later stage. So we were actually very happy that the wing was stronger than we designed it for. So that allowed the 21 meter case. Right, so the crash test is another tricky story. Then you have to demonstrate with the new CS22 rules is that you can take an impact of 9 Gs into the ground. The old certification standard was 6 Gs. But since 2009, a new requirement is that the aircraft must take a 9G load. Now, because we are a new applicant, we have to use the latest standard and we have to do the 9G test. Where all the aircraft that you've been flying, the modern ones, are only on 6Gs because they can use the grandfather certificate, type certificate. So if you buy a new aircraft now from any manufacturer, it's only designed to 9Gs. But if it's an aircraft that's been certified after 2009, from a new model, not a modification to an old type certificate, it has to have 9Gs. Now I think this is the only aircraft, this one and the Shark, that complies to 9Gs. I think I'm correct with saying that. In any case, you have to have 9 times of the Gs, and then you have to simulate a 45-degree crash and a 5-degree side angle. Now you can see what our test rig looked like. So we designed the test rig, and then we have the fantastic carbon piece of fuselage that we're going to throw away after this exercise. And if you can see there, we have a load cell in the bottom at 5 degrees, and then we have some hydraulic pumps to pull this fuselage into the ground. Okay, so if you can see the picture from the side, there we start to apply a force on this hydraulic actuator, and you can see the nose start to crash on the fuselage. Now what must happen? What is the desired result? The desired result is that 9 Gs will be, of the fuselage, will be supported by the structure without damaging areas where the pilot's vital organs are. So in front of the legs forward, it may fail and should fail as a crumple zone, and the upper body must be protected. Right, so let's see what happens. So if you have a video here, let's try to fly. It's a horrible sound. It sounds like, what was I doing? Until that point, then you can see the first failures start to occur on the sides here, and after, you must just get this mouse to work, and on the top section there, you see the side sills are now failing, and from there the aircraft will be failing. Okay, so how much did this actually mean? If you look on the load diagram, this is time, and this is the loads that we applied, and that 1.1 safety factor, we have to achieve 1, and it's a safety factor of 9 Gs. Now the total load on that nose is 6.5 tons. Now imagine that, because it's 720 kilograms, multiplied by 9 Gs, it's 6.5 tons that was required on that nose. Now I have a pickup car term. Now it's a bakkie. What do you call a pickup here? You know, a pickup. Now my pickup is 1 ton rated if you apply the 1 ton over the axles. If I put 2 tons on it, it's tough, the wheels will explode. Now imagine 2 meters away from the attachment point, you apply 6.5 tons. Just imagine how strong a fuselage is compared to a car, like a pickup. It's unbelievable. Right, and then flight testing, this is more where I was involved in. You have to demonstrate handling and performance, stability, and you have to develop the envelope. Now typically, what you first have to do, we have to develop a system where you actually lock the data. So this is our first system, and the first one, you see there's an iPad there locking the information. You have some flight test sheets where you write all the information from the test down, and we have cameras. If you see the camera sitting there, there's cameras on the wing, on the side, to determine, so that once you land it, you can demonstrate to the authorities that you actually made the test, that you have made it. Now there are various tests. For example, you have to demonstrate stall speed, show that the stall speed is below a certain number. You have to demonstrate certain stall characteristics. It may not be dropping wind too rapidly without the ability to recover it. You have to be able to transit from any flight configuration with anyone without difficulty. So there's lots and lots of details, and that's where we lock it. Now recently we've developed with Alex Naff an integrated flight recording system which works fantastic. So the information that we log in nowadays is just unbelievable. But even this old one that we developed was quite good. So we'll show you a few of these, how we did it. It's a flight computer with batteries and a system. It's basically exactly how the LX9 system, LX9000 also works. So basically what you do, you lock the data and you push an event number. It means it starts recording and give an ID number to a specific test. Once you land it, you download this file of data, and you're going to check for the test, and you look on the graphics if you did make the test. Okay, so this system we basically developed, and the LX1 is exactly the same. You'll see then on all the sticks you have sensors. For example, that's the rudder pedals, to measure what is your control inputs. And that is on the stick and on the elevator. So elevator, stick and rudder has got sensors, and you'll recognize this from a company in Slovenia, these flap encoders. not too far from where we are now. Right, and then we have cameras for some of the videos, and then obviously if you look, I think this might be a video, yeah, you can see some in this case was a flutter test, when you fly the thing at VD. In this case for the 21 meter we only had to go to 300 kilometers an hour, with the 80 meter we had to go to about 330 kilometers an hour, and then you have to simulate flutter. So you have to hit the stick, you have to shake the stick, you have to kick the stick, and you have to find natural oscillating frequencies which the ground vibration set will be problems. So first you do a ground vibration, you shake the whole aircraft from the ground for all frequencies, and then this is going through a fantastic program, and they tells you this frequency and that frequency on this is critical, so in flight you have to go and simulate those frequencies, you have to actuate it somehow. So here you will see some of the 300 kilometers, so don't do this at home. If you look at the airspeed, what did you push to this way? I just want to have the pointer. So if you see the pointer there, it's sitting there, there's VE, and we're sitting there 30 kilometers above VE. And then you shake. So you go through all the control systematically by giving a pulse inputs and the frequency sweep. And you see now we will do also the natural oscillation frequency will be coming now. And this is all while you're eating up height at the alarming rate. You see that is just stuck there at -5 meters per second of this way. And you can see that specific one was a flutter mode in this direction, and we tried to oscillate the frequency and see if this can get out of hand and break the wings off. Hopefully not. And the last test is that you have to demonstrate that there's no control force, control reversal, so that at high speed that you don't suddenly, controls are acting differently to what you would like to have. So this is typically a high-speed test that you have to do. You see we're running out of height and then you have to abandon the test. Doesn't look so funny in this case, but when you fly at this high speed, you know, nobody's flown there, you sometimes wonder if you've done it correctly. Right, now typically from our logger, we can see this is the speeds that we are flying here. Our true airspeed was about 375 kilometers an hour. And you can see here is where you give the frequency sweep, where you shake the aileron, and there is where you give it the pulse input, where you hit the aileron. You can see this is the control input and the speeds, and you can immediately see the damping as well. So you can see that the aircraft is well damped. Now if you give the authorities this type of pictures, they understand, okay, it's flutter free. But if you just tell them that yes, it's flutter free, they always ask you, how can you show that? Right, one of the requirements that's also interesting to show you is the spinning. It's part number 221. Now, just a few interesting facts about this JS1C certification. There are thousands of combinations of spins. Spins with air brakes in, aft CG, water, half full, empty, landing gear in and out, half tanks, full tanks. So there are so many combinations that you put all these combinations down, and with the authorities you select different combinations. And those are your critical spins that you're going to have to do. Now we selected 44 different type of spins. And some spins you enter in this mode, some you enter stick in, stick out. So lots and lots of these you have to do. Now for the 21 meter, we have to complete 86 complete turns. We probably lost about 15 kilometers of spinning height. And we spent about 7 hours behind the tow plane to get to altitude. So that just gives you an idea how expensive spinning is. You know, it's a real expensive exercise. Which we did not include here, was the number of underpants that you had to throw away after some of these tests. So I should have actually also said so many underpants is also required. It's horrific, some of these tests, because you do it for the first time, you move the CG back, and at certain stages this aircraft is really very, very keen on spinning. You know, it loves spinning. And you don't allow it anymore. You do control inputs and it doesn't behave as you actually want to have it. But you have to determine the aft CG, what is safe for the pilot, and then you move this well forward and you say, okay, this is what you have. So if you see your aft CG range, be sure that we have tested it well behind that. But don't fly it well behind that, because you don't know where we stop. Okay, so I just have a small video on spinning. I hope it will go. So this is a specific spin exercise. I think I'm going to play it twice because you can see different things.
5-10 spin, extended brakes, landing gear.
Okay, so it's a 5-10 spin, air brakes extended, landing gear extended, fully loaded. So this aircraft is at maximum all-up weight 720 kilograms in the worst configuration, aft CG plus a lot more. You see, we started at 2,000 meters AGL. What is interesting to observe is the first turn how high it will go above the horizon. Now air brakes open. Any sharp pilot would have realized that I pulled out too tightly out of the spin and I dropped the wing to the right side. I don't know if you saw that. Just play that again. You'll just see. If I would like to show you what you can observe, what is quite interesting. If you could look at what the airspeed indicator does, because of the side yaw, the airflow over the pitot is so at such an angle that you see actually a zero airspeed. So first check how your airspeed is fluctuating. In real life, your airspeed is not fluctuating. It spins at a fairly gentle speed of about 90 kilometers an hour. But because of the changes of yaw, the airflow over the pitot is so that you register zero airspeed. The second thing that is actually real is the yaw string. If you look what the yaw string is doing, that's actually what the flow is doing over the aircraft. So it's a really, really unstable situation, which is good, because if it's a stable spin, you will not recover easily. So what's the airspeed and what's the string this time? So the airspeed is now about 80, 90, and 98, zero airspeed. So you see how bad your indication is. Look what the yaw string is doing. It's fluffing all over the show. Left, right, in, out. And you can see how we eat up altitude. And there I dropped the wing to the right. So we lost almost 1,000 meters in this 5-10 spin. It's quite amazing. Now, once you analyze the data, you can draw some nice graphs. This is what the spin graphs look like. First, you have your control input. That's your elevator. You can see I kept the elevator all the way back until we recovered. The second, this is the heading. You can see that the heading is consistently almost the same rate of change. So you can see we have done 1, 2, 3, 4, 5 turns. That is the altitude is on the next slide. I'll show you the altitude on the next slide. And here is the aileron input. It was a spin with neutral aileron. So you can see, okay, aileron was neutral. And the rudder, you see, it was full rudder input until we did the recovery. So you can see the recovery started at that point, and then you have to demonstrate that the aircraft can recover from a spin within one turn. And if it's less than half a turn, you can also certify it for spinning. So this aircraft is fully certified for spinning because it recovers within half a turn. Right, that's the altitude profile. We started at 11,500 feet and we recovered at this position here. And you can see from the recovery point, we can determine what is the altitude loss. And this is actually the G's. See, while you're in the turn, can you see how the G's is actually building up? And this is the reason why the authorities want you to do a 5-turn spin. Because within the turn, things are getting slowly more and more vicious, if I can call the word vicious. You can see how the G is changing and going up. And after 5 turns, it was at quite some 2.5 Gs. Within the spin, you have 2.5 Gs. Quite amazing, huh? One wouldn't think that. So what I would recommend is that one is really, if you're comfortable with the instructor, that you do these spins and do the recovery so that you understand the behavior of your aircraft, the behavior of the Gs and the sensors, so that you don't do something stupid by hanging on into the stick. And just a small piece, I think you've all done an instructor's course this morning where you've had some refreshment on that. Just remember one thing, if you're flying and the aircraft wants to go nose down and you pull the stick back, you prohibit it from doing an automatic recovery. So whenever you're in trouble and you let go of the stick, it will fly automatically self. But if you prevent automatic nose pitch down and you hold the stick back, you prevent it, it is destined for a spin, most aircraft. Good. I don't have the slides of the next two projects that we're doing on, so I'm going to cut my presentation short here. And I would just say our slogan is that our performance is unbeatable and the experience flying it is a revelation. So I thank you for the time and effort and listening to me, and I appreciate to be here. Thanks very much.